Welcome to the PowerBlog site. It is Monday, June 11th, 2012. This evening we're bringing you our finding about the high radioactivity that was detected in South Bend, Indiana on June 6th and 7th. We've reanalyzed the data, and the data pretty well, almost conclusively in our opinion, shows that the Geiger counter did experience a highly radioactive field high enough to saturate the Geiger counter. Now, we're going to go over this quickly in technical terms, just for the people who understand this, and hopefully we'll try to disprove this. And then we will go into easier to understand, simpler detail. But in essence, what we have is, and I'll get ready to show you the chart, there's a bimodal clipped peak feature on the chart with the dropout, shown in the 5-hour-long radioactive detection from a radioactive field saturating the Geiger counter. Let me show you the detection here. Now, this is the chart of the actual detection, and if you can see, the chart displays from June 4th through June 10th down here. So this is a pretty wide spread. So this is over 5 hours worth of detections here, putting in a very tight spot. But what you'll see is that there's a ramp up, and then quickly the Geiger counter goes nonlinear, and we have a peak where saturation occurs, and then we have a dropout for an extended period of time, and then we come up with a subsequent peak when the saturation event ends and the Geiger counter comes back down to normal readings. And then down here at the very bottom, we've got about a 40-minute stretch where the Geiger counter read normally. Now, what's interesting is in South Bend at this time period, there was there was a 5-mile-an-hour wind that stopped right 5-mile-an-hour wind out of the north that stopped approximately 11:30, and then immediately thereafter this detection started. The detection ended at approximately 4:20, and it just so happens that a 5-mile-an-hour wind picked up out of the west around 4 a.m. that morning. So these peaks are surrounded by weather phenomena on either side that basically defend their presence. I'm going to zoom in here real tight just to make this easier to see and show you what we have going on here with these peaks, just so you can more clearly see the saturation point. And here's the first peak, and this is basically where the saturation point started at 1:48 a.m. And then if you notice here that this peak here is a little bit lower, we have some hysteresis going on here, and this peak next appeared at 3:27. So from approximately 1:48 to 3:27, this Geiger counter was reading close to no radioactivity. And because of the hysteresis, there is a little bit of noise in here, we believe, when it was coming back down. So that's in essence our explanation. Now, one other key finding out of this situation is that there was a reported tripping of a ground fault interrupt circuit on an outlet. And now, we can't verify that. The rest of the data we can verify because it exists in graph form and it's out on the internet. But we have a report of this ground fault interrupt, and then an eventual shutdown of a backup power supply. And we believe that the ground fault interrupt could also have been tripped by a high radioactive field, specifically beta radiation, which is basically electrons that could interfere with the ground fault interrupt. So that gives us basically a double-handed approach that really backs us up. So we have a relatively simple explanation that covers the entire detection. We don't believe that there's a simple power failure circuit mode explanation that can describe this detection window. Now, what we've done is model these peaks. And let me show them to you here in Excel. Alright. So here's the peak in the same basically perspective as reported on the Black Cat Systems website. And here's our model of this peak, showing linearity, non-linearity as the radiation goes up, saturation point down here in the red, another non-linearity on the other side from hysteresis coming down, and then the linear trail, and then going back out. So we've got a pretty good approximate here. Now the way we developed this is we took a Weibull curve fit, and we fit that curve to either side of the saturation point down to the starting point and to the end point. And when we do that Weibull fit, let's see, basically this is what we came up with. So this is a Weibull radiation intensity chart that mimics the fallout detected on either end of the saturation point and at the end points, and mimics it very well. Now, what I've done over here on this right hand side is I've taken the time steps in the chart and put them on the time steps of the actual detection and put them against the Weibull distribution. So right here in the distribution is where the saturation point started in the real detection. Right here is where the saturation point ended, and here's our point of non-linearity, both on the front side and the rear side of the detection. And then here's where the Geiger counter was working as it should. Now, one thing you'll notice is we have these counts per minute in question mark. We're not exactly sure what the units are, but the Black Cat Systems site listed them on as counts per minute, so that's what we labeled them as. So now we'll go in and compare the environmental reading. This is our Weibull environmental radiation estimate, and this is how this estimate would look on the Geiger counter. Now when you compress this in time, basically what you end up getting is this peak chart here, which looks like the original detection. So we'll go back to it. Now the key thing here to look at is while the Weibull fits this half of the detection and this half of the detection very well, time-wise there's you can see it's not balanced, and we believe this saturation is not balanced because of a hysteresis in the detection. Now, if you are apt to believe that a Geiger-Mueller tube doesn't experience hysteresis, then what this would mean is that this red line should be actually like start here and stop here. And what that means is that this peak is nowhere near high enough. So if one is to believe hysteresis doesn't occur on a Geiger-Mueller tube, then this Weibull was not fit well, at least from the peak perspective. So this peak in reality could be much higher. Now what happens here in the tube, and now this is where we go into our simplified explanation. And so first let's explain what makes a Geiger counter count. What happens is a bit of radiation comes in and hits the tube, and then it goes, basically hits the tube, so the tube detects when the radiation hits and detects when the radiation leaves. So you've got an on and an off. So every time there's an on and off in the tube releases one click. Now what a lot of people don't understand is that the tube physically requires a short moment of time to reset so it can prepare for the next click, for the next radiation event. So what happens is, as the radiation goes higher and higher, and the tube gets hit faster and faster by radioactivity, there comes a point where the Geiger counter can't reset itself fast enough to detect the next radiation event. And that's when the readings start to become nonlinear. It's actually a sampling rate problem, sort of equivalent to a Nyquist frequency issue. But basically what it means is that every one radiation event no longer equals one increase in reading. So you may have multiple radiation events show up as only one click. Then it reaches a point where the radiation events are coming in so fast that the Geiger tube just can't reset ever. It never resets. So all it gets is the on signal. It never gets an off signal saying that the particle is left. So a click, a detection, is an on and an off signal. And if it gets so many hits that it never has a chance to rest so it can turn off for that split second so it can get the next signal, then it basically thinks it's only got one detection. And what happens then is you go from a very high radioactive reading to your Geiger counter reading close to 0, even though the radiation level is really high. And that's because it just is getting hit by so much radiation that it can't reset itself. So it only comes across as one click. And that's what that's called saturation. And that's this point in the reading. And then what happens is the radioactivity starts to drop, and then you get back into the nonlinear region, which is you still might have several radiation events come through the Geiger counter, but it only picks them up intermittently because it's still recovering, it's still resting. And eventually it recovers enough that it goes back to functioning normally. So that's in essence what we have in this detection in South Bend, Indiana, is we've got a peak that comes up normally. It's strong, but it's normal. And then we have an area of detection where it's nonlinear, and then all of a sudden it just drops out to 0 or close to 0, and then as the radiation starts dropping, it starts to be able to function again. Then eventually it drops enough where it can start to function normally. And that's why if you look at the real graph, and let me go here to the real graph. And I've zoomed in on this real graph real close, but we'll go down here to the bottom. If you look down here at the bottom, right down here. So this is when the wind stopped blowing, and then right around here, right around 4 o'clock is when the wind started blowing again and the radiation started to move out. So if you see we're right around 4:30, and then by 5:04, the radiation levels are back to normal background readings. So there's like a 40-minute span here after the wind started where the radiation level goes back to normal. And then the equipment shuts off until 4:41 in the afternoon. Now doesn't look like anywhere during this time period that anybody messed with it. There's no indications that the equipment was shut back on or off. It followed the weather pattern, increased, saturated, and decreased. So this is an extremely strong indication of a true detection. And we don't believe that there's a power supply phenomena that can easily explain the totality of this detection. Now, what threw off our gut instincts initially is we heard the claim of a power failure. And so instead of thinking about this thing as a Geiger counter and a Geiger-Mueller tube, we started thinking about this thing as just an electrical circuit. And we saw this clipping where it cuts off at. It cuts off here and here. And clipping does occur on circuits when there's a circuit failure and it gets just too much, let's just say it's energized too much and it can't do any more, then it cuts off. But then you would expect a square top. You wouldn't expect this dropout. You also wouldn't expect the other dropout to be less. It should be flat topped. So that's what threw off our gut reaction, was thinking of this as a power supply circuit instead of thinking of this as a Geiger-Mueller tube, which is exactly what you're seeing here. And that's why there's a saturation point where it basically drops down to nothing. So as we said, this is a really strong indication of a true detection. Now the other thing that had crossed our minds previously was, well, this could be a real detection. It blew in, blew out, and then blew back in. But of course, there was no wind. Wind charts show no wind for this 5-hour time period. And then one would have to question, well, why would it blow in, leave, go to 0, and then blow back in at nearly the same level? That seems a little bit inconsistent. In reality, what it is going on here is this Geiger counter was saturated and couldn't detect anything, and then it came back, and then we got the real detection. So that's in essence what we've got going on here with this. Now let's look at the wind data real quick. So, this is the evening of June 6th, and over here on the right we have June 7th. Since this reading spanned midnight, we got to go both nights. And if you look here at approximately 11 o'clock, you can see the wind was blowing about 5 miles an hour, and it was coming from due north. Now if you go over to 12 o'clock, you see there's no wind direction listed because there is no wind blowing. And if you look at the wind speed chart, you'll see that there is no wind speed given because the wind's not blowing. And if you follow the wind speed chart, the wind doesn't start blowing again till 4 o'clock. And then at 4 o'clock, the detection shows as the wind's coming out of the west. So there's just a 1 hour span there where the wind picks up for 5 to 5 miles an hour for probably at least half an hour and comes out of the west. And then the rest of the day, for the rest of these 4 hours, it doesn't blow anymore. So we have a really strong indication here of this detection being basically a stagnation point in the atmosphere where the radioactivity built up. Now we'll look at the jet stream. Now this is the jet stream from 6 p.m. on June 6th. I believe the time difference here is about 6 hours. And you can see the termination edge of the jet stream right over here over South Bend, Indiana. And so we're going from an area of high wind to an area of lesser wind. So when you've got that stopping, you can have stuff fall out of it, basically fall out of the jet stream. So that's one of the things we are looking at, is this detection possibly coming on the jet stream. And we'll go to the jet stream map now from, this is from 6 a.m. on June 7th. And you can see the jet streams actually move further on south, away from South Bend. Now the first report of a message coming back from the station's radiation operator who took these readings was 7:45 a.m. Now there are some incongruities in here, but it's just a short report, and sometimes it's not easy to explain everything quickly. Says he has no idea what shut it down. He says he shut down Geiger graph and restarted it, but there's no indication of that anywhere in the time period where the detection was occurring or for the 40 minutes after the detection ended. So we don't know when that happened, but it doesn't look like it happened anywhere during that graph we showed you. Also says that a GFI, ground fault interrupt, tripped. Now what a ground fault interrupt does is basically it's one of those things that you got on your hairdryer that keeps you from being electrocuted if it falls in the water. And basically what it detects is a small leakage of electrons between the ground wire and the rest of the circuit. Well, it just so happens beta radiation is electrons. So it's potentially possible that this ground fault interrupt was shut off by a high level of beta radiation. Of course, gamma and alpha radiation could probably muck around with it too. But so this ground fault, if it occurred, I mean, we don't have evidence that it occurred, we don't have any verifiable evidence other than the report here. There's no graph or data that shows that this actually occurred. But it is reported. So, if we go back to our chart here, you can see that this is actually, excuse me, a very good approximation of what occurred here in South Bend. And it's very concerning to us. But basically, what we've done here is shown that the simplest explanation that explains all the circuit behavior and all the other behaviors are an actual highly radioactive field. So now the question is what does this come down to? What do we do about it? Well, we've discussed that slightly here, and that is that the key steps forward are, and this should have been done immediately after this detection, is that sample swipes should have been done in and around the specific area the Geiger counter was. That means around the house, anywhere where radioactive material could build up. If this was a cloud of iodine of some sort, a volatile radioactive material, then it would leave residue behind that could be detected. If it was a noble gas that blew through, then you're not going to detect it from a swipe. But this should have been done. And it's just amazing to me that there's been, we waited the whole weekend to think about and go through this data, and there's been no follow-up from anybody associated with this that we're aware of. Specifically, they should identify the specific detection location with at minimum, a 5-mile area. We don't know where in South Bend this occurred. The map shows it occurring at the airport, but that doesn't necessarily mean that's where it occurred. If we had some idea reasonably where this is, you could start looking for potential culprits. You could look at the lay of the land. You could see what could make this happen. We also don't know the specifics of the Geiger counter and the associated setup. That would tell us a lot about the potential for supersaturation. It also would give us an idea of how high the field was, because if it's a known model or a known tube that's got data on it, then we can determine at what level it would saturate. But these two things, knowing the detailed location of the Geiger counter and the setup and what type of Geiger counter it is, that should be inherent information given out on these radiation detection websites. It just should be there. We should know that right away so you can investigate. And the other thing we would call to ask to do is, since this was quickly explained off the cuff as a potentially being a power failure. Oh, we had a high radiation reading and we had a power failure. So obviously this is from the power failure. Well, that's the easy answer. It's also the answer that protects your credibility, because nobody wants to say there was a high radioactive field and have a chance of being wrong. Of course, that also puts people at risk. If this was a failure of the power supply or some voltage source, then they should attempt to replicate this. But this was a 5-hour-long detection. If somebody can replicate this on a power supply, or even explain how you could get this saturation condition as shown with a power circuit failure, I'd like to see it, because there's no simple explanation that I'm aware of out of there that can do this readily. And if there is, I want to see somebody prove it. Now, the possible conclusions we have out of this is, first of all, we don't know how large or small this radioactive detection was. We know it was hot, but we don't know if it was a massive cloud or just a small cloud, a release from a nearby source. We don't know. If we had some idea where the location was, you could look around the area. But our possible conclusions are that the airborne fallout was from a small but very radioactive source near the detection location. A near source scenario would likely be southeast of the location, and that's based on the north wind stopped blowing. That allowed the gas to fill in, and we assume it's a gas, to fill in and start the radioactive detection. Then when the wind started blowing out of the west, it blew it clear of the detection area. Now, so that's our, given a near source, is our most likely location. It's also possible that the source was located north of the Geiger counter. But what that would mean is that this radiation came in on the last puff of northerly surface wind and allowed it to settle out there, because the wind stopped and then the radiation detection started. So we give that a little bit less scenario. Another conclusion is that a far source scenario, and that would be that the fallout came out of the jet stream. Yes, it is possible for radioactivity to come out of the jet stream even at these levels. Some people who are in industry would even tell you, these levels are nothing to worry about. But no, it's not impossible. It's a fluid flow problem. And it's not impossible for these things to occur at this level. And what makes it strangely concerning to us is, here in St. Louis, we also detected a 5x airborne radiation detection after a rainstorm. There was no rain in South Bend when this occurred. We had a 5x airborne detection here in St. Louis, which caused us to release a maximum alert. Along with that, we discovered that there were other detections all along the North American continent of higher airborne detections. And there have also been detections now in Europe, all following the jet stream. And you take along with that the detections of iodine-131 in incineration ash and a dried sewage sludge in Japan, you've got a case here. So this event in South Bend occurred during a period where the Potterblog site had listed a maximum alert for radioactivity in the jet stream and staying out of the jet stream. So that's the essence of it. You know, the thing is that if you've got higher radiation, a lot of Geiger counters will fail. And they just can't handle the higher saturation points. You need a Geiger counter specifically designed to handle that kind of radioactivity. And that'll bring us back to the Geiger counter we showed you the other day. Old com block Soviet model here. Now, as soon as the light comes on, I'll show you. There we go. Yeah. And this, as I said last time, this model has 3 settings. It's got crying, which is 0.5 rem an hour, frying, which is 5 rem an hour, and dying, which is 30 rem an hour. This type of Geiger counter, as com block simple as it is, can detect highly radioactive fields. You don't want this thing going off. The question is would this have gone off in South Bend? It's possible.